Hey everyone, how's it going? This is Siri and I'm back with another PyTorch video, and in this video we're going to be starting to dip our toes a little bit into the actual learning process. Up until now we've been talking about tensors, we've been talking about the different tensor operations, and we've talked about the different types of data that we might encounter in our machine learning journey. And what else did we talk about? Yeah, I think that's pretty much it, right? We talked about tabular data, we talked about images, time series, and other interesting stuff. But today, although this video is going to be pretty short, right? We're going to be going through the entire process. We're going to be going through a description of the entire process. We're not going to be doing any of the implementation, and we're not going to be diving into each of the different steps just yet. We're going to be going back, way back in time, before, computers were invented, before all of this, technology disrupted our, daily lives and everything, right? We're going to be going back to the 1600s. The 17th century, and it's going to be interesting, and we're going to be talking about where this whole idea of training a model came from. What does it mean? Everyone says, hey, my machine learning model's learning from the data, or yeah, I'm training my model. What does that mean, right? So we've talked about how we have an input, right? In machine learning, we have certain inputs, and our whole goal is to learn from whatever data that we have. And I know I'm generalizing this again, but we're going to be going into it, just be patient. So we have, inputs, they're paired with outputs, they're paired with outputs. And the model's goal is to, predict an output based on a new input, right? That's expected, right? We have f of x is equal to x plus 2. This is the pattern that we learned. We learned that whatever output we're going to have, it's going to be the input plus 2. And if I pass in a completely new thing that the machine has never seen before, it's going to be able to apply what it's learned, which was x plus 2, and say, hey, this is going to be 4 plus 2, we're applying it, and we get a prediction. And our prediction seems to be accurate. So that's kind of actually what happens, right? It's rooted in math. This is a very, very simple example, but you'll see that the reality of, machine learning isn't too far off from this. We have some other complicated, stuff, right? But it's all based on these mathematical functions. And once you seem to get your head wrapped around that, from there it's pretty, the idea is pretty easy. I mean, applying it to a real world example is another beast, but we'll tackle one thing at a time, right? So the question is, what is the algorithm behind this entire learning process? What algorithm are we talking about? An algorithm is just a series of steps you take to get to the place that you want, right? In simple terms, right? So what is that algorithm? Well, let's go back to Johannes Kepler, You'll see that this is incredibly close. Actually, it's exactly the same as what we do with machine learning and deep learning. So Johannes Kepler, he's an important figure in the scientific revolution, and he came up with the 3 laws of planetary motion. So it's all about space and the object in space, planets, right? And that's what he's best known for. He's best known for these planetary laws, these laws of planetary motion. And so he uses basically the steps that we use or rather we should say that we use the steps that he used back in his day when he, learned more about this planetary motion and came up with these 3 laws. So what did he do? First of all, okay, we'll get to the laws at the end, but what did he do? What did he do to get these 3 laws, and how did he approach this? Okay, so first of all, he had tons of data. Okay, he had tons of data, and he had it from his friend. Okay, and right, it wasn't without some struggle. He had to work a lot to get this data, but he has some data. Okay, just like we have data, right, in machine learning. It's like a data-driven methodology. So he tried to visualize it first. Okay, so the visualization. Okay, he tried to visualize the data that he had. He didn't have computers, so it was all on pencil and paper. So, he tried to do some graphs and, tried to get a sense of what his data looked like. Okay, on like a coordinate plane and things like that. Okay, because he knew that there was something going on here. He obviously didn't start off with the 3 laws, right? So he has some data and he made some observations. Okay, first he had some observations and then tried to visualize it because he thought that there was something interesting going on. Okay, and he chose a simple model at the beginning to start. You gotta start somewhere. You can't start with the most complicated thing ever, right? Well, let's just start with a simple model and see if that visualizes things and that works with new data. But we're not there yet, right? So we choose a simple model, okay, that he thought would, fit the data. So what does this mean? Okay, let's clear up some terminology here. What do I mean by fit the data? Well, fitting the data, right? If you've ever heard of a best fit line, right? You have like a scatter plot, sort of, and you have all these dots scattered across the your coordinate plane. So you have your X, you have your Y, and you have some data, and you plot it, and you see some sort of trend. It's not exactly like that, right? But we have some sort of fuzzy trend going on, and the line that you draw to try to approximate that trend is, is that best fit line. So, okay, I'm trying what I can here. Okay, this isn't working, but maybe, let's check it out. Best fit line, right? So, we see some points, this fuzzy sort of thing, but then we draw a definitive line that, tries to approximate that. So, for example, if I want to go here, if you see my mouse, I want to approximate what that value is. I go up, okay, and I go to that line, and that's my approximation. Okay, so that's what's going on. And, yeah, so, it's best fit line. Okay, trend line. You could think of it as that. Okay. Okay, so now we have some visualization. We have the data that we're visualizing. We have a model, okay, mathematical model. Okay, it's a function. It's literally a function, except in our case, we're going to have a bunch of functions. But here, right? We just have a function. It's a simple mathematical model. And it's a model, right, because we can model new data, and it just represents that, it models it. So that's why we call it a model. So he created a model that he would think would fit the data. And what did he do next? Well, he has some data, right, and he has a way to represent that somehow. So now he broke up his data into two piles of massive data. Okay, massive amount of data. Actually, he took his massive amount of data, let's rephrase that, took his massive amount of data and broke it up into two parts. Okay, and those two parts were, first, you want to have some data, right? First of all, you need to have, okay, not everything's going to be like a line, right? So we want as many points as possible, although not all of the points, but we want as like half the points to go into visualizing and modeling the data. So this line is a model of the data. We're representing it. And so if we have some more complicated data, then we're going to, approximate it in a different way. So we take half of that data, which is still a lot of data because we have a ton of data to start out with. And so we break it up. Okay, one is to train it, which is basically fitting it. Okay, fitting the data, finding the trend. Okay. And one is for testing the data. Okay, so making sure my model / representation / trend that he thought it was actually accurate. Okay, so he wants to check that. So we have some test data. So this is like the 4 in our f of x. Okay, so we have some new data and to check, hey, is this actually, what I want? Is this actually the model that represents the data best? Okay. If you use all of the data for training, how are you going to know whether your data works or not, right? So, so you need a way of making sure that what you're doing is good, what you're doing is accurate. So that's why we have a test data. Okay, so what did he do next? Well, what he did next was so what he did, right, well, first he thought that it was an ellipse. Okay, so he thought that this sort of function would be elliptical. Okay. Kepler thought it would be elliptical. Okay. So he doesn't actually know the eccentricity and the size, right? Those are, like, if you've studied ellipses, you know that they're two, like, focus points or, like, foci, and, you have some, rational functions that go along with it, and, okay, whatever, right? So we start off with an initial eccentricity and size, okay? And so we actually don't know how the ellipse is going to look. We think it's an ellipse, but we start off with an initial, like, 2 attributes for the ellipse. So if it were a circle, then we would pick some 2 random points for values for our center and our radius. Okay, so except this is an ellipse, so we have 2 different attributes here. So we start off with an initial one, but we're going to soon know that we're wrong, right? We had no basis for coming up with these values, and we just chose one because we have to, right? We have to start somewhere. And yeah, so we pick an initial value and we roll with it. But we roll with it so that we can learn from it. And so this was an iterative process, okay? Okay, let me put this in all caps. This was an iterative process, okay? What do I mean? Well, like, okay, if you're familiar with iterations, right, in a loop, right, you keep going and going and going until a condition is met, or until, like, however many times you want it to go, we're gone. So you loop through it, but at each time you loop through it, you're going there for a purpose, right? So the purpose that we're looping through this is to get better, is to make our model, is to make these different values, the eccentricity and the size, we want to make them perfect, okay? We already think it's going to be, an elliptical model, so we're going to roll with that, but we need to fix the perfect or close to perfect attributes. So this is where the iteration goes and comes from. So this is an iterative process to get the best eccentricity and size. All right. And yeah, so once he was done, and once he said, hey, okay, I think this is good. I think these are two good attributes for my elliptical model. Now is the point to validate the data. Okay, this basically is the testing phase. This is part B of number 4. So we're actually using that test data. Validate the model and the eccentricity and size on the test data. Okay, this is also called the validation set, because we're validating on it, right? We're making sure that it's correct. So yeah, he did this based on his own observations. But now we have a model, right? We have a computer to let us know whether it's actually correct or not. But here he used his validation set and he basically validated it on his own, right? He used his own observations to check whether it worked or not. So part number 7, we have the 3 planetary laws of motion. It's actually laws of planetary motion, so let's not get it mixed up. And so this video, what am I saying? Okay, these laws were, okay, let's put like triple exclamation point here and just smile, because now we have the 3 laws of planetary motion. Okay, these 3 laws were, okay, I'm just saying this for fun, okay, so these were his results. So the first one was that every planet's orbit is an ellipse with the sun at its focus. So every ellipse has a focus point, right? So every planet's orbit is an ellipse with the sun at a certain focus point. 2, a line that connects both the sun and a planet sweeps out equal areas at equal times or in equal times. And the third one is that the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. Okay, so every ellipse has a major and minor axis. If you're familiar, okay, if you're confused, don't worry. Okay, I'm not an expert at astronomy either. But if it makes sense to you, then that's great. Okay, but the main points to note are like these 7 steps. Okay, these are essentially what's going on behind this learning process. This is the algorithm. Okay, these are the steps you need to take. Okay, and PyTorch has the tools to help us with this algorithm. And since our models, our data might not, fit nicely to an ellipse, right, or any other, like exponential or linear, any of the things that we can, or elementary functions, right? Or I think the term was transcendental functions, or anything that we can express. If it's nothing that we can express easily, then we have some more complicated things going on, and neural networks helps us with that. And that's that mathematical web that I keep talking about, right? You see the math behind this, right? It's f of x equals x plus 2. Maybe it's not as easy as that, but it goes along the same lines as it. And the only difference is maybe it has some more non-linear functions, and it has more functions in general. And it does more things to the inputs and outputs to make sure that our trend is getting approximated properly. And yeah, so that's what's going on behind this. And we took Kepler's example just as a fun way to learn about this process. Motion and how it's essentially the same as the machine learning process. Okay, so we'll talk about each of these steps in detail in our next few videos, and we'll start off with our data and gathering data and visualizing it and things like that. Okay, and then we're going to be moving on to the neural network part, the interesting part, and we'll learn more about that then. Okay, so hopefully and hopefully this demystified this whole machine learning thing for you, and it's not magic, it's just math. It's math that you and I can do. Actually, maybe it's not, but, it's built off of that foundation. And so yeah, I think that's basically it. I hope you learned something new, and I hope this got you excited. I hope you learned something, and yeah, don't forget to like, comment, and subscribe. I'm looking forward to seeing you in my next video.